Dear students, welcome to EPG Pathshala. Today in this module, we will be discussing about radioactive waste, its definition, sources, classification, segregation, treatment and various disposal options. The learning objectives of this module include the basic understanding of radioactive waste, the sources from which they are generated, their classification, segregation, and finally we will look into the treatment and various disposal options of radioactive waste. To begin with, what are radioactive substances? Radioactive substances are those which emit ionizing radiations in the environment. They have wide applications in many fields, starting from power generation to industries to medical centers and research centers. These applications generate radioactive waste. Now, why it is important to manage these radioactive waste is that they are hazardous and they emit radiations. These radiations are harmful to human health because they cause cancer in human beings. Hence, it is essential for us to manage this waste in a proper and safe manner. As mentioned earlier, radioactive substances are those that emit ionizing radiations. They are categorized as hazardous waste because their prolonged exposure leads to radiations causing damage and death of living organisms. They persist in the environment for a long period of time. The period in which radiation occurs is commonly measured and expressed as half-life. Half-life means it is the time required for the radioactivity of a given amount of a substance to decay to half its initial value. Since the discovery of radioactivity, it has found its application in various nuclear energy utilizing programs and activities. There are basically two types of nuclear reactions which occur. One is nuclear fusion and the other one is nuclear fission. Nuclear fission is nothing but an atom is divided into smaller or lighter atoms numbering 2 or more. In nuclear fusion, fusion happens when small atoms 2 or more join or fuse together to form a large or heavy atom. Both these processes involves the generation of nuclear energy that results in vast amount of energy and radioactive elements. Now, all these processes results in the generation of radioactive waste, and radioactive waste are defined as waste products which emit nuclear radiation and are contaminated with radionuclides at high levels of activities or concentration beyond the established permissible limits with no anticipated use. They are generated during operation, maintenance and decommissioning of nuclear and radiation facilities. Radionuclides in the waste may exist in either solid, liquid or gaseous form depending on their physical and chemical properties. They need proper management in a safe manner to protect human health and environment from the effects of ionizing radiation. Now, let's look into the sources of radioactive waste. Now, radioactive waste are generated from nuclear power plants. As we all know, in recent times, nuclear energy is gaining more importance because of depletion of fossil fuels. Next important source from where radioactive wastes are generated is hospitals, including veterinary medicine. The radioactive substances are used in radioassay, clinical diagnosis and radiotherapy. Next, the biomedical research facilities also use these radioactive waste in developing and labeling of radiolabeled compounds, study of metabolic, toxicological and environmental pathways of various drugs, pesticides, fertilizers and other chemicals. Test animals, when involved, also result in radioactive substances in their excreta, carcasses and bedding. Further, the clinical process development and testing also results in generation of radioactive waste. From industry, the radioactive substances are generated from oil exploration and well logging, quality control, water treatment, sterilization, food irradiation, luminous devices and electronic valves. These radioactive wastes are also generated from smoke detectors and lightning rods. In defense also, these radioactive substances are used in gaseous tritium lights, equipment and instruments coated with luminous paints. Now let's look into the classification of radioactive waste. Based on the safety assessment for disposal site and radiological classification, radioactive wastes are classified as exempt waste, which is designated as EW. This is defined as waste that meets the criteria for clearance, exemption or exclusion from regulatory control for radiation and protection purposes. These classifications are provided by IAEA. IAEA is nothing but International Atomic Energy Agency. Second type of classification is very short-lived waste, which is designated as VSLW. These are waste that includes waste that are short-lived with short half-lives. They are used in research and medical purposes. They can be stored for decay over a limited period, that is up to few years, and later disposed of as uncontrolled disposal. Next type is very low-level waste, VLLW. The waste that does not meet the criteria of EW, that is exempt waste, and do not require a high level of containment and isolation is categorized as very low level waste. They are suitable for disposal in near surface landfill type facilities with limited regulatory control. Examples of this type of waste include soil and rubble with low levels of activity concentration. If the concentration of longer lived radionuclides in very low level waste are generally very limited. Next type of classification is low level waste, designated as LLW. Now, waste containing long lived radionuclides in little amount and is above clearance level. These are categorized under this particular waste. It also includes short-lived radionuclides with high concentration. These wastes require isolation and containment for periods of up to a few hundred years. Now, disposal for this particular waste should be done in a safe, engineered landfill near surface facilities. The next classification is intermediate level waste, designated as ILW. Now, wastes that require complete isolation and a greater degree of containment are included in this category. They contain long-lived radionuclide and emit alpha radiations. Disposal should be done at depths of the order of tens of meters to a few hundred meters. There is no need of any provision for heat dissipation when intermediate level waste are disposed of. The last category of radioactive waste is high level waste, which is designated as HLW. Long-lived radionuclide and waste that possess high levels of activity with concentration high enough to generate significant quantities of heat during the radioactive decay process are included under this category. These wastes are more harmful and hence should be disposed in deep and stable geological formations, usually several hundred meters below the Earth's surface. Now, we will look into the management aspects of radioactive waste. Radioactive waste contaminate air, water, soil, and consequently vegetation that eventually affect public health and environment adversely. According to IAEA, the principles of radioactive waste management are: first, protection of human health, protection of environment, protection of national borders, protection of future generations, burden on future generation, national legal framework, control of radioactive waste generation, management interdependencies, and safety of facilities. Radioactive waste should be separated according to their isotopes. All other isotopes must be placed in separate containers except for tritium and carbon-14 that can be placed in same container. This is how radioactive wastes are segregated. There are 10 basic physical forms of radioactive waste which are identified. First one is solid, glass, sharps, liquid scintillation vials, biological, animal remains, source vials, lead picks, and sealed sources. Now let's look into the various treatment and disposal options of radioactive waste. The purpose of treating radioactive waste is to reduce its volume. The nature of treatment always depends on the quantity, radiological and physiochemical properties. Solid and the liquid waste is segregated and given separate treatment. The different types of treatment provided are discussed below. The treatment of solid waste, treatment of liquid waste. Under liquid waste, they are categorized as aqueous and organic liquid waste. Organic liquid waste will include liquids, solvents, oils and other biological fluids generated from nuclear research and medical centers. Now, what are the treatment options which are available for solid radioactive waste? Now, before treatment, the solid wastes are segregated into combustible, compactable and non-compactable forms. The purpose of solid waste treatment is to reduce the volume of waste and make it suitable for storage and transport. The process used include, first one, shredding. The waste will be reduced or shredded into small pieces. This will reduce the void space and is particularly effective when wastes are to be compacted. Second type is crushing. This is used for size reduction of friable solids. Examples of friable solids are glass, concrete, ceramics, etc. Normally, mill, grinder and crushing machines are used for crushing these waste. The third type is cutting. This is done for items like metals or plastics. The size is reduced for storage, transport or incineration. The cutting is done either in the dry state inside the cells or with conventional tools under water. Plasma jets, laser torches or explosive fuse cutting are also used for cutting the solid radioactive waste. Now, compaction is one another type the solid wastes are treated. By this process, volume of waste is reduced and concentrated. The volume reduction to a factor of 3 to 10 can be carried out by this process. Conventional and super compactors are generally used for compaction process. In conventional compactors, plastics, paper, absorbent material and cloths are compacted, whereas in super compactors, metal, pipe, wood are compacted. Now, after these preliminary steps, the material is incinerated. Incineration is a process where the waste is combusted at high temperature of around 900 to 1100 degrees Celsius. It reduces the volume of waste by 90% and the end products produced include ash, carbon dioxide, water, sulfur dioxide, oxides of nitrogen and HCl gases. Since it reduces the volume of waste by 90%, it minimizes the requirement of the land for disposal of waste. Now, incineration is used for reduction of both solid and liquid radioactive waste volume. Now, the limitation of this process include it requires an off-gas filtering system. Second, a pre-treatment is also required. Example, thickening and dewatering of liquid waste. Dewatering is nothing but removing the liquid part and the solid part is used in the incineration process. It also involves high cost because this process is energy intensive. The emission control units are to be fixed in these incinerators to control particulates, sulfur dioxide, oxides of nitrogen and other products of incomplete oxidation. This will also minimize the problems of air pollution. And finally, the last limitation include volume of secondary waste generation is also very high from incinerators. Now, let's look into the treatment options of aqueous liquid radioactive waste. The treatment process involved in treating the aqueous liquid waste are discussed below. First treatment process is ion exchange or sorption. In this process, the cations and anions are exchanged or replaced between an insoluble solid matrix containing ionizable polar groups and a liquid solution. When the ion groups are negative, the exchange will involve cations, and when they are positively charged, they involve anions. Ion exchange is a reversible process and these exchanges or exchange resins can be regenerated. If the exchanges is saturated, then they are replaced with new resins. The old exchange resins are then treated as solid radioactive waste. The materials in general which are used as ion exchange resins include natural ion exchangers and synthetic materials. Clay, zeolite, cellulose, charcoal and collagen are examples of natural ion exchangers, and zeolites, hydrous oxide gels of metals or organic resins formed by highly polymerized cross-linked hydrocarbons containing ionic groups, example sulfonic acid, carboxylic acid, amino groups, etc. are categorized as synthetic ion exchange resins. The next type of treatment option is chemical precipitation. Under this, the low and intermediate level radioactive wastes are treated. They are used for removing waste with low and intermediate level radioactivity that are produced from fuel reprocessing facilities, research laboratories and power stations. This method is simple, economical, with a large potential to treat huge amount of liquid effluents. This process also requires pre-treatment such as pH alterations, oxidation of organic contaminants, decomposition of complex species and alteration of ionic species. Next type of treatment process for treating aqueous liquid radioactive waste include evaporation. Evaporation, as you all know, it is a process of concentrating the waste where it can reduce large volume of liquid waste. It is used for high, intermediate and low level waste effluents. They are generally performed in commercial evaporation units. The limitations of this process include they are unsuitable for waste effluents that contain large concentration of inactive salts. Secondly, they are also expensive due to high energy requirement. Sometimes they lead to explosion due to the presence of organic compounds in the liquid effluent. Certain membrane processes are also used for treating aqueous radioactive waste, which includes ultrafiltration and reverse osmosis. Now, let's look into the various treatment options for organic radioactive liquids. Now, liquids, solvents, oils and other biological fluids generated from nuclear research, medical centers are treated under this category. The waste can be radioactive, biohazard or a chemical biohazard. The purpose of this process is to reduce the volume of radioactive waste so that it can be safely stored, transported, conditioned and disposed. The process used for treating organic liquids are discussed in the next few slides. The first process which is used for organic liquid radioactive waste is incineration. I have already discussed about incineration in the previous slides. Again, incineration is nothing but a process where a waste is burnt at a high temperature of around 900 to 1100 degrees Celsius. It reduces the waste by 90% and it results in the production of ash, carbon dioxide, water, sulfur dioxide, oxide of nitrogen and HCl gas. Since it reduces the percentage by 90%, the land requirement is very less for disposal of waste. Again, the limitations of this process is they require off-gas filtering system. You need to install emission control equipments for controlling these particulate matter and gaseous pollutants. Second, they are also energy intensive process which involves high cost and it releases or generates a huge amount of secondary waste. It also requires pre-treatment such as thickening and dewatering of liquid waste. Next type of process is wet oxidation. Wet air oxidation is similar to incineration, but only difference is the temperature used is very low compared to incineration, where a temperature of 900 to 1100 degrees Celsius is used. The process involves oxidation of pollutant through injection of an oxidizing agent inside the reactor. Mainly, the oxidizing agents used include hydrogen peroxide, activated sodium persulfate, ozone and Fenton reagent. Fenton reagent is nothing but hydrogen peroxide in combination with iron as a catalyst. The end products include carbon dioxide, water, oxygen, small proportions of non-toxic ions, salts and acids. Waste such as organic contents of radioactive waste from ion exchange resins and foams, cellulosic waste and liquid scintillation waste are treated using this process. Next is acid digestion. Acid digestion is also popularly used for treating organic liquid radioactive waste. It is an oxidative destruction technology for organic liquids like hexane, oil and organic constituents of mixed waste such as cellulose, rubber, polymer such as polyethylene, polyvinyl chloride, polystyrene and other resins. During this process, the waste volume is reduced by 20 to 100 times. This process involves use of an acid mixture. Acid mixture is nothing but nitric acid is mixed in phosphoric acid as a carrier solution. The temperature and pressure used for this acid digestion process is 200 degrees Celsius and a pressure of less than 20 psi. The end products that are generated at the end of this process includes inorganic constituents and gases such as carbon dioxide, carbon monoxide, oxygen and oxides of nitrogen. Distillation is another process which is used for its treatment. And as you all know, distillation is a chemical process by which the substances are separated from a liquid mixture by selective evaporation and condensation. The process provides high decontamination efficiency. It is also a volume reduction technique. It is used for treating liquids that are generated from scintillation counters and solvents from other equipment. The advantages of the distillation process is they are simple and cost effective if the solvents are recycled. Now let's look into the various disposal options of radioactive waste. In the management process, disposal is the final step. High-level nuclear waste from both commercial reactors and defense industry present a difficult problem to the scientific community as well as to the public. The solution to high-level nuclear waste are still debatable both technically and ethically. There are numerous proposals for disposing of high-level nuclear waste. However, the most favored solution for discarding the radioactive waste is sorting out radioactive waste from man to avoid unwanted radiation exposure. Thus, the radioactive waste is confined or isolated from the biosphere in the repositories. The location of repositories is decided based on the longevity and concentration of radionuclide present in the waste. Always the repositories can be near the surface or in deep geological formation. Now these are the various options that are available for disposal of radioactive waste. As mentioned earlier, the option is chosen based on the nature of the radionuclides. The options include deep geological repositories, underwater disposal, that is ocean dumping, which is mainly done by seabed burial or sub-seabed disposal. Next is subductive waste disposal method. Next one, it's by transforming the radioactive waste to non-radioactive stable waste. Finally, it is a solar option, which is nothing but dispatching to the sun. These options require serious studies and technical assessments. Now let's look into these disposal options in detail. Now first one, the geological disposal. For handling long-lived radioactive waste, disposal in the form of geological disposal in deep geological formations are used. Whether it might be under continental crust or under seabed, this method has been recognized since 1957. Deep geological disposal involves introducing waste packages in underground structures in an impermeable geological medium having favorable properties in terms of geological stability, hydrogeology, geochemistry and response to mechanical and thermal stress. The chosen media must avoid areas of exceptional interest, that is underground water resources, and these structures must be located at least 200 to 300 meters below the ground surface. This will avoid the effects of erosion and human intrusion. This picture depicts the geological deposition. You can see the radioactive wastes are deposited below 300 meters. Here the wastes are contained in canisters and then they are buried at this depth. The deep geological sites offer a natural isolation from the system. They can be stable over thousands of years to hold long-lived radioactive waste. The low-level radioactive waste is normally disposed of near the surface or in old mines. Likewise, the high-level radioactive waste is disposed in host rocks that are crystalline or salty or tough. In countries where high level radioactive waste is minimal, always there is a provision for storage facility. Once the collection is over, then it can be disposed of. Second type of disposal method is underwater disposal. In underwater disposal, normally the spent nuclear fuels are disposed of in underwater. The underwater disposal is done by two methods. One, dumping containers of radioactive waste into the ocean, and second one is sub-seabed disposal. The main reason of using this underwater disposal for spent nuclear fuel is to isolate them from human contact and the environment for a long period of time. This might avoid the release of harmful radiations. See, this figure shows how the nuclear waste are sealed in these canisters and then buried in the underwater. Now, this method is being used by many industrial countries like USA, France, Great Britain, etc. They have been dumping the radioactive waste in oceans, which they consider to be a least expensive method. Especially USA, they have dumped around 1,12,000 containers of nuclear waste at 30 locations in the Atlantic and Pacific Ocean. USA has stopped sea dumping of spent nuclear fuel since 1980s. Although the practice has been prohibited by many countries, Russia, which is producing almost 60% of world nuclear energy, still continues to dispose of its nuclear waste into the ocean. Next type of disposal is sub-seabed disposal. Seabed disposal is different from sea dumping. It does not involve separation of low-level radioactive waste within geological strata. The deep ocean floor is a part of a large tectonic plate situated 5 km below the sea surface, and it covers around hundreds of meters of thick sedimentary soft clay. These sections are usually deserted. It looks like desert and it supports no life. Thus, such areas are chosen for sub-seabed disposal. Sub-seabed disposal is complex and it involves two methods. One, creating a repository with the possibility of retrieval of spent nuclear fuel, and second one is everlasting burial. This is next type of disposal option. Transmutation of high-level radioactive waste. Transmutational devices that consist of a hybrid of a subcritical nuclear reactor and an accelerator of charged particles are used to destroy radioactivity by neutrons. Destroy cannot be the proper word. What is effected is that the fission fragments can be transmuted by neutron capture and beta decay to produce stable nuclides. Transmutation of actinides involves several competing processes: neutron-induced fission, neutron capture, and radioactive decay. A large number of neutrons produced in the spallation reaction by the accelerator are used for destroying the radioactive material, which is kept in the subcritical reactor. This scheme is not been practically demonstrated so far, and it is not cost effective. This is the next type of disposal method. It is called a subductive method. This is the latest technology in waste disposal, the radioactive waste disposal. It is a single feasible means of disposing radioactive waste that guarantees non-return of relegated material to the biosphere. Simultaneously, it affords inaccessibility to abolished weapon material. The principle behind this is it eliminates the material from the biosphere as faster or as earlier as possible. It is considered the safest, the most sensible, most economical, most stable long-term, most environmentally benign, and most completely obvious place to get rid of nuclear waste, high-level waste or low-level waste in deep oceans that cover 70% of the planet. Subduction process is a process where one tectonic plate slides beneath another and is ultimately reabsorbed into the mantle. The subductive waste disposal also follows a similar method, where high-level radioactive waste repository in a subducting plate so that the waste will be carried beneath the earth crust, where it will be diluted and dispersed through the mantle. If you see, the rate of subduction of a plate annually is around 2.1 centimeter. This is considered to be the slowest subduction zone. This is faster than the rate of diffusion of radionuclides through the turbidite sediments that would overlay a repository constructed in accordance with this method. The subducting plate is naturally predestined for consumption in the Earth's mantle. The plate is continuously renewed at its originating oceanic ridge. The slow movement of this plate would seal any vertical fractures over a repository at the interface between the subducting plate and the overriding plate. The last option is solar option. It is proposed that the surplus weapon, plutonium and other highly concentrated waste might be placed in the Earth orbit, and then it can be accelerated so that the waste would drop into the sun. Although it is theoretically possible, it involves vast technical development and extremely high cost compared to other means of waste disposal. It is a robust waste containment, and it is required to ensure that no waste would be released in the event of failure of the space transport system. So now this table will summarize the different classification of waste, from where it is originating, and finally the disposal options. In previous slides I have already mentioned about the low level, intermediate level and high level waste, and also the different disposal options are given here. To summarize, today we have discussed about the radioactive substance, its ionizing radiations, the harmful effects, also the application in which the radioactive substances are used, and how radioactive wastes are generated from various sources. Now, after this, we have also discussed about the classification of this radioactive waste as provided by IAEA. Later, we also discussed about the various treatment and disposal options, where the disposal options are always near the surface or below, deep below the earth surface. It can be below the earth surface or it can be under the water. From this module, you can understand the seriousness of radioactive waste and the importance of disposing it off in a proper and safe manner. Thank you.